1 minute ago, instruments buried beneath the Italian town of Pozzuoli recorded another tremor. The seismographs barely flinched. Magnitude 1.8. Unremarkable by most standards. But for the scientists monitoring Campi Flegrei, this earthquake carried a different weight. It wasn't just another shake in a restless caldera. It was a crack forming, a fracture spreading. Evidence that the crust beneath 500,000 people is no longer bending under pressure, it's breaking. And when rock stops bending and starts breaking, everything changes. This isn't speculation. This isn't sensationalism. Published research from Italy's National Institute of Geophysics and Volcanology, confirmed by international teams at Stanford University and the University of Pisa, reveals that Campi Flegrei has entered a new phase. The ground is fracturing at depths of 2 to 3 kilometers. A volcano-tectonic fault is being born beneath the streets of Naples. And while no one can say with certainty what comes next, the message from deep underground is unmistakable. Something is building, and the Earth's crust is running out of room to absorb it.
Campi Flegrei doesn't look like a volcano. There's no towering cone, no smoking summit visible for miles. Instead, it hides in plain sight, a vast caldera stretching 12 to 14 kilometers across the densely populated Bay of Naples. The name translates to burning fields, a reference to the steaming vents and bubbling mud pools that have dotted this landscape since ancient times. More than 360,000 people live directly on top of the caldera, their homes resting on ground that has risen and fallen for millennia in a phenomenon known as Bradysseism. But Campi Flegrei is more than restless terrain. It's a supervolcano, capable of eruptions that reach the highest levels on the Volcanic Explosivity Index. About 39,000 years ago, it unleashed the Campanian ignimbrite eruption, spewing 200 cubic kilometers of magma and blanketing much of Europe in ash. Another massive eruption followed 15,000 years later. Then, after thousands of years of relative quiet, it erupted again in 1538, forming a new mountain called Monte Nuovo in just 1 week. That eruption was preceded by years of seismic unrest and dramatic ground uplift. Witnesses reported the ground rising by as much as 20 meters before the crust finally ruptured, burying the Roman village of Trappergole beneath torrents of ash and lava. For nearly 5 centuries, Campi Flegrei slept. But in the 1950s, it began to stir again, and it hasn't stopped since.
Since 2005, the ground beneath Pozzuoli, the town sitting at the center of maximum deformation, has been creeping upward relentlessly. By the end of June 2025, total uplift reached approximately 1.48 meters, based on GPS monitoring at the Rioni Tedra station. Nearly 30 centimeters of that occurred in 2024 alone. At first, scientists observed what they expected: elastic deformation. The crust stretched like a rubber band, bending under pressure from fluids accumulating below. Earthquakes occurred, but they were small, diffuse, scattered across the caldera. The rock was straining, but it was holding. Then in 2021, something shifted. Seismic activity changed character. Instead of random scattering, earthquakes began clustering along a distinct geometric plane. Researchers analyzing data from 2023 and 2024 identified a fault plane striking at 249 degrees, dipping at 53 degrees, concentrated beneath the Solfatara Picciarelli area. More than half of all seismic events and most of the released energy now align with this single structure. A study published in Communications, Earth and Environment in October 2025 made the conclusion explicit. This is no longer just bradysseismo. A volcano-tectonic fault is nucleating beneath Campi Flegrei. The crust is transitioning from elastic bending to inelastic fracturing. When researchers from Roma Tre University and INGV described the findings, their language was precise but grave. The rocks are no longer responding elastically. They're breaking. And that fracturing, they suggest, indicates the crust has reached conditions that could lead to critical failure.
The earthquakes themselves tell the story. In 2025 alone, more than 6,400 seismic events were recorded near Campi Flegrei. Most were small, magnitude 2 or less, but their frequency and location painted a troubling picture. On March 13, 2025, a powerful earthquake struck at 1:25 in the morning, jolting residents from sleep. The tremor, with its epicenter just 2 kilometers deep beneath Pozzuoli, was one of the strongest the region had experienced in decades. Then, on May 13th, another magnitude 4.4 quake rattled the caldera in a dramatic swarm that included 49 events. But the most powerful came on June 30, a magnitude 4.6 earthquake at a depth of 4 kilometers, described by authorities as the strongest recorded at Campi Flegrei in 40 years. Buildings cracked. Residents fled into the streets. Civil protection teams deployed immediately to assess damage. There were no fatalities, but the psychological impact was profound. For people living above a restless caldera, every tremor is a reminder that the ground beneath them is not stable. It's alive, and the patterns suggest it's breaking. Seismic swarms became increasingly common. Between February 15th and February 19th, 2025, more than 690 earthquakes rattled the caldera in a single burst-like sequence. Another swarm struck in late August and early September, with 94 events in less than 24 hours, including a magnitude 4.0 quake on September 1. These weren't isolated incidents. Based on the clustering patterns and increasing frequency, they appear to be symptoms of an accelerating process deep underground.
What's driving this fracturing? The answer lies in a weak layer of rock discovered by researchers using advanced seismic tomography and experimental analysis. Published in AGU Advances in April 2025, the study revealed a critically damaged zone at depths of 2.5 to 3 kilometers beneath the caldera. This layer, weakened by repeated magma intrusions over thousands of years, acts like a sponge, trapping gases and fluids rising from deeper magma chambers. As pressure builds, the rock reaches its breaking point. Cracks form. Faults slip. Earthquakes ripple outward. But the fracturing isn't random. Artificial intelligence analysis conducted by Stanford University researchers uncovered hidden patterns in the seismic data. Traditional methods had cataloged about 12,000 earthquakes between 2022 and mid-2025. AI revealed the true number, 54,000. 3/4 of the seismic activity had gone undetected. When researchers mapped these previously hidden earthquakes, a stunning structure emerged, a clear, crisp ring fault encircling much of the caldera. This ring fault, combined with the newly forming volcano-tectonic fault beneath Solfatara, suggests the caldera may be reorganizing itself structurally. If this interpretation is correct, the reorganization could have consequences no one has witnessed in nearly 500 years. Another discovery added urgency to the scientific picture. Researchers at the University of Pisa and the GFZ Helmholtz Center in Germany identified long-period seismic signals never before recognized at Campi Flegrei. These signals, known as Very Long Period or VLP events, indicate the presence of fluid-filled, crack-like structures resonating deep underground. The waveforms and spectra of these signals have remained remarkably stable over recent years, suggesting a persistent pathway for gas to escape from depth toward the surface. This resonance process, coupled with shallow fracturing, creates what could be a feedback loop. As gas rises and pressure fluctuates, the surrounding rock fractures further, triggering more earthquakes and releasing sudden bursts of energy. Residents near the Solfatara crater have reported hearing loud booming sounds during seismic swarms. Scientists attribute these explosive bursts to steam flashing as liquid water rapidly vaporizes during fault rupture, a process confirmed in laboratory experiments. The ground isn't just shaking, it's venting, and with each release, the structural integrity of the overlying crust may be weakening further. At Stanford University, geophysicist Tiziana Venorio led experiments that replicated conditions beneath Campi Flegrei in a laboratory setting. Using a hydrothermal vessel that functioned like a stovetop espresso maker, her team demonstrated how cracks in the caprock above the geothermal reservoir sealed themselves through mineral precipitation. Within 24 hours, fibrous minerals formed and closed the fractures, creating a pressure cooker effect underground. Fluid pressure builds until it exceeds the rock's strength, triggering sudden fracturing and steam-driven explosions.
The cyclical process, documented during both the 1982 to 1984 unrest and the current episode, points to a recurring pattern. But there's a critical difference this time. The cumulative stress accumulated since the 1950s suggests the crust may be closer to catastrophic failure than during previous episodes. Professor Christopher Kilburn from University College London, who has been tracking Campi Flegrei's behavior since 2016, warned that the volcano has been moving steadily toward rupture. His team predicted that after an additional 30 to 40 centimeters of uplift beyond 2016 levels, the crust would reach critical stress levels. That threshold has now been crossed. The ground beneath Pozzuoli has risen well beyond that point, and the fracturing has begun.
The human dimension of this unfolding crisis is impossible to ignore. Approximately 500,000 people live in the red zone, the area designated as high risk for pyroclastic flows in the event of an eruption. This zone includes the entire municipalities of Pozzuoli, Baccoli, Monte di Procida, and Quarto, along with portions of Naples itself, including neighborhoods like Soccavo, Pianura, Bagnoli, and Fuorigrotta. Beyond the red zone, more than 800,000 people live in the yellow zone, exposed to significant volcanic ash fallout. Italy's National Civil Protection has developed an evacuation plan requiring the removal of the red zone population within 72 hours if the alert level reaches the alarm phase. The plan involves buses, trains, and ships transporting residents to twinned regions across Italy. Pozzuoli residents would be evacuated to Lombardy. Those from Baccoli would go to Umbria and Marche. Monte di Procida residents would head to Abruzzo and Molise. It's an enormous logistical challenge. The plan also includes a pre-alarm phase, potentially lasting months or years, during which voluntary evacuation is encouraged. But how do you convince 500,000 people to leave their homes, their livelihoods, their entire lives, based on probabilities and uncertainties? In September 2024, Naples City Council unanimously approved the updated municipal evacuation plan, a document that city officials emphasized was not about the current Brady seismic crisis, but about preparedness for a potential volcanic eruption. The plan was drafted with what Councillor Edoardo Cosenza called a prudent approach, acknowledging that while volcanic risk exists, an eruption is not imminent. Still, the approval came at a time when residents were feeling the ground shake beneath them with increasing frequency. Trust in evacuation plans depends on clear communication, transparency, and confidence that authorities can execute the plan effectively. But doubts linger. Critics have questioned whether evacuating 500,000 people in 72 hours is realistic. Would the transportation infrastructure hold? Would receiving regions be prepared to absorb such a massive influx? And what happens to those who choose to stay, either out of skepticism or inability to leave? On November 6, 2025, Italian authorities conducted the Campi Flegrei 2025 exercise, testing the maritime evacuation route for the first time. A sample group of 120 students and 15 teachers from a Naples school participated in a simulated evacuation from the port of Naples to twinned regions in Sardinia and Sicily. The exercise aimed to verify procedures, coordination between agencies, and the functionality of infrastructure. But an exercise with 135 people is vastly different from evacuating 500,000 in the chaos of a real emergency. The parallels to 1538 are haunting. Before Monte Nuovo erupted, residents of the area witnessed years of escalating signs. The ground rose, the sea retreated as land emerged from what had once been water. Seismic activity intensified, with 20 tremors felt on September 28th alone, the day before the eruption began. When the eruption finally came on September 29th, it opened with hydromagnetic blasts as water interacted with rising magma, sending surges of hot ash and debris racing across the landscape. The eruption continued for a week, building a 123-meter-high cinder cone from the ashes of Tripergole. By October 6th, after a final, fatal explosion killed 24 people who had climbed onto the new mountain, the eruption subsided. Fumarolic activity continued for decades, but the main event was over. What had taken years to build released in days. Today, the ground beneath Pozzuoli has already risen more than in the years preceding the 1538 eruption. The earthquakes are more numerous. The fracturing is documented in ways that 16th century observers could never have imagined. And yet, the outcome remains uncertain.
Uncertainty is perhaps the most difficult aspect of volcanic unrest for both scientists and residents to manage. Campi Flegrei could continue in its current state for years, even decades, releasing pressure through small earthquakes and gradual deformation without ever erupting. It could enter a new cycle of subsidence, as it did after the unrest of the 1980s. Or the fracturing could accelerate. The fault could rupture fully and magma could find a pathway to the surface. Volcanologists stress that rupture of the crust is a necessary but not sufficient condition for eruption. The magma must be in the right location, with the right pressure, at the right time. Seismic data so far show no clear evidence of magma migrating toward the surface. Most earthquakes remain shallow, above 4 kilometers depth, concentrated in the hydrothermal system rather than indicating magma ascent. But the absence of magma migration today does not guarantee its absence tomorrow. The cumulative stress built up since the 1950s means that even relatively weak signals, such as a smaller rate of ground uplift or fewer earthquakes, could precede an eruption. This was the case at Rabaul caldera in Papua New Guinea in 1994, where an eruption followed seismicity occurring at 1/10 the rate of a crisis a decade earlier. Monitoring continues around the clock. The Osservatorio Vesuviano, part of Italy's National Institute of Geophysics and Volcanology, operates a dense network of seismometers, GPS stations, gas sensors, and thermal cameras across the caldera. Every tremor is recorded. Every millimeter of ground movement is measured. Gas emissions from the Solfatara fumaroles are analyzed daily for changes in composition that might signal deeper processes. Temperature sensors track fluctuations in hydrothermal activity. Satellite radar interferometry maps ground deformation with precision. The data flows in continuously, feeding into models that attempt to forecast what might happen next. But forecasting volcanic eruptions remains one of the most challenging problems in earth science. Volcanoes are complex, dynamic systems influenced by factors we can only partially observe. The structure of the crust, the distribution of magma and fluids at depth, the pathways available for gas escape, the mechanical properties of rock under stress, all of these variables interact in ways that are difficult to predict. What scientists can say with confidence is that Campi Flegrei is changing. The transition from elastic to inelastic deformation is real. The fault forming beneath Solfatara is real. The ring fault identified by AI is real. And based on fault geometry and scaling relationships, researchers suggest the potential exists for a magnitude 5 earthquake, larger than any yet recorded at this volcano. The broader implications extend beyond the immediate region. Campi Flegrei is one of the most closely monitored volcanoes on Earth, precisely because of the population density and the potential for catastrophic impact. If scientists can better understand the processes driving its unrest, the lessons learned here could improve forecasting at other calderas worldwide. The same techniques being applied at Campi Flegrei, from AI-driven seismic analysis to laboratory experiments simulating crustal behavior, are being tested at volcanoes like Santorini in Greece, Long Valley in California, and Yellowstone in the United States. Each of these systems poses unique challenges, but the fundamental question remains the same. How do we distinguish between unrest that will subside and unrest that will lead to eruption? Answering that question requires not just better technology, but a deeper understanding of the physics governing volcanic systems. And it requires humility in the face of uncertainty, acknowledging that despite all our instruments and models, the Earth still holds secrets we're only beginning to uncover.
For the residents of Pozzuoli, the science is secondary to the daily reality of living above a fracturing caldera. They feel every earthquake. They see cracks spreading in the walls of their homes. They hear the booming sounds from Solfatara. They watch the sea recede as the land continues to rise. And they live with the knowledge that the ground beneath them could rupture at any moment, or might remain stable for generations. It's a psychological burden as real as the physical risk. Community meetings have become more frequent, with officials attempting to balance transparency with reassurance. But reassurance is difficult when the data shows a crust in transition, a fault being born, and a supervolcano that is awakened after centuries of sleep. Some residents have already left, seeking homes beyond the red zone. Others remain, either by choice or necessity, tied to the land by history, family, and livelihood. They've adapted to the tremors, the evacuation drills, and the omnipresent awareness that they live on borrowed time. And in that adaptation, there is a kind of resilience, a refusal to be defined entirely by the volcano beneath their feet. Campi Flegrei is a reminder that we live on a dynamic planet, one where the forces that shape continents and oceans operate on timescales both geological and human. The crust beneath Naples is fracturing because of processes that began tens of thousands of years ago, when massive eruptions hollowed out the Earth and created the caldera. Those ancient events left scars in the crust, zones of weakness that now trap rising fluids and concentrate stress. The earthquakes shaking Pozzuoli today are echoes of forces unleashed millennia before anyone lived here. Yet they are also intensely immediate, affecting real people, real communities right now. This tension between deep time and human time is at the heart of volcanic hazard. We build cities on volcanoes because the soil is fertile, the landscape beautiful, and the risks seem distant. Then the ground begins to shake, and distance collapses into immediacy. Scientists cannot yet say whether Campi Flegrei will erupt. They cannot predict the timing, the magnitude, or the style of a potential eruption. What they can say is that the volcano is sending signals. The crust is fracturing. A fault is forming. Pressure is building in ways that appear to mirror the conditions before the 1538 eruption. The monitoring will continue. The research will advance. The evacuation plans will be refined. And the people of Naples will keep living, working, and hoping that when the Earth finally decides what comes next, they'll have enough warning to get out of the way. The story of Campi Flegrei is not over. It may not even be at its climax, but one thing is certain. Something is happening beneath the surface. Something we can measure but not yet fully understand. The fracturing has begun. The crust is breaking. And whether that breaking leads to catastrophe or merely another chapter in this volcano's long, restless history, the world is watching. Because when a supervolcano wakes up in one of the most densely populated regions on Earth, the stakes are too high to look away. If this story left you thinking about the power and unpredictability of our planet, subscribe to Eruptions now. We bring you the science behind the spectacle, the data behind the drama, and the stories of the people who live in the shadow of Earth's most restless places. The ground beneath us is always moving. Stay informed.